All right, guys, we ready to get started? That's a yes, perfect. All right, so give me a quick reminder before we get into our guest speaker of what we talked about last week. What's that? We talked about bridges? That's correct, we played with bridges, but more specifically what we were talking about last night. Civil engineering, what was that, Dustin? You had it. Civil engineering, somebody said the right word. Engineering mechanics, thank you. So what was the whole point of engineering mechanics? As far as how we were looking at it last week. Yes, we looked at shapes, right? So good. So why is, and you made it with your hand, right? Why is the shape important? Yeah. So we talked about. Remember we did the pencil example, right? We had the triangle with the pencils. So if I have this engineering structure, and I press down on the top of it, is this engineering structure under tension or compression? Well, so the structure on itself is under what? Compression, right? And now you guys are skipping ahead to the example, right? But if I didn't have this bottom member, what would happen to my triangle? It would just collapse, it'd fall flat, right? So these guys are being pressed, and this guy's working together to do what? To hold them apart. So this guy's under what? And that's what you said, right? This guy's under tension. Okay? So we looked at engineering mechanics, or we looked at mechanics last week in terms of mostly statics. And why is statics important from what we're trying to do from a civil engineering standpoint? You can say it louder. Yeah, because we don't want things to move, right? If things move, or rather if we have an unbalanced force, remember F equals ma. If we have an unbalanced force, what happens to my structure? It accelerates is the word I'm looking for, but yes, it moves, right? And do we want our building to within, we're okay if it maybe moves in the wind a little bit, right? But do we fundamentally want our structures to move? The answer is no, because that's when our bridge falls down. Yes, sir?
So if you were building a car, then you would want to use the dynamic fit instead?
Well, maybe. When your car is traveling at 55 down the road, is it accelerating? Is it not accelerating? Is it a constant velocity, right? And you also want your car to stay together, right? I mean, we actually talked a bit about orbital mechanics last week, right? Which is actually a case where we have constant acceleration because remember our vector is changing, right? But we want it to stay in the same orbit so that it doesn't go flying off into space, right? I saw a hand back there. No question? All right, so if there's nothing else, I'd like to introduce my good friend and fantastic, fabulous engineer. This is Mr. Nick Besson.
Thank you.
So let me give Nick a little intro. Nick got his bachelor's in electrical and electronics engineering at Oregon State. He now works at Eaton, where you've been for 10 years, right?
10 or 11, yep.
10 or 11. So he holds the title District Operations Supervisor, so he's a pretty big wig at Eaton. And what he's going to do tonight is give you guys a little talk about what he does, some projects he's worked on, and then let you guys ask him some questions about what he does on a day-to-day basis in the field. So if you can please welcome Nick.
Thank you. Good evening. Thanks for having me here. I'm very impressed the number of you here to learn about engineering on your evening. So what I'm going to do is walk you through my background and hopefully give you perspective on an engineering career path that's different than what you might have heard about before. And actually, I've never served as a practicing engineer. So hopefully I'll give you a little bit different perspective on what you can do with an engineering degree. And then I'll briefly go through an example engineering project that hopefully you'll find interesting. So to start out with, how I got involved in engineering, like a lot of you, I enjoyed math, science, computers, technology in high school. I wouldn't say those were my best subjects or I was the best at them in my school. But when looking at college, college is a significant investment in both time and money, and I was interested in something that would have a high likelihood of employment afterwards. So that's how I chose to go to Oregon State and get into electrical engineering. And when I was there, I decided that what I wanted to focus on specifically was power systems engineering, which is the study of how you distribute power and use it for purposes like heating and lighting this building. And the reason I did that was probably twofold. At the time, there was a lot of excitement and development around renewable energy, electric vehicles. Weren't really into the concept of smart grid yet, but there was a lot more focus on how we get and use our electricity and how we can do that more efficiently. The other thing that stood out to me was there weren't a lot of people that were going into that field. So things like microelectronics and semiconductors, computer engineering, there were a lot more students that were focusing on those, and I thought it would be smart to maybe go where other people weren't, which I think has benefited me. I was able to do a couple cool things at Oregon State, one of which was getting involved with the Wave Energy Research Program as part of my senior design project. So Oregon State has a great and has had a great power systems program. I was fortunate to be able to participate with. When I was approaching graduation, I didn't really have any clear direction, wasn't sure where I wanted to go to work or if I wanted to stay in school and potentially get a graduate degree. And I happened to stumble upon the engineering career fair the term that I was graduating, and was pulled aside, had my resume looked at, and was asked to interview for a position with Eaton where I currently work in technical sales. And I had never thought about a career in sales or even really know what that meant. But as part of the interview process and learning about the company and the position, I really felt like it was a great opportunity for me. So when I started with Eaton, so Eaton is a company it's a manufacturing company, and we manufacture power distribution equipment. Basically any place where electricity is used or moved between the point of generation at the utility plant and to the point of use or the point of load, like this classroom. We make products that help other companies safely move and protect their electricity. So my job as a technical sales engineer was to work with customers that were specifying or buying that equipment and help make sure that we were configuring the best product for their application. And I would encourage everyone that I talk to, if sales can be looked at as not a professional occupation and certainly not but in a field like power distribution or power systems, the way that you help your company sell products is by understanding the technical aspect and the application better than the other people in the industry. So it was a great way for me to use my technical background, my engineering degree, but also be in a position where I could interact with people and help really learn more about business and use a whole different skill set, not just the technical side, something I really enjoyed. I also, after working as a sales engineer, moved into a position called application engineer, which is really more of a regional technical expert. And in that role, I was focused more on influencing the design community, consulting engineers, governing bodies, things of that nature. A lot of giving presentations. I've provided testimony for the state building codes division, the Association of Electrical Inspectors, things of that nature. In my current job as operations supervisor, I essentially run an engineering business. So while I work for a manufacturing company, we have what's essentially sort of an independent consulting engineering business. So I have engineers that perform studies, evaluations, as well as go out and physically work on power distribution equipment in the field. So we could be working at anything from a commercial building, a building downtown, hospital, data centers, utility plants, really anywhere where power is used. And so in this job, I'm managing the financial aspect, the operational excellence, building the capability through developing the people on my team, as well as looking at ways to grow and manage our business. So while it's a deviation from where I sort of started with my degree as engineering, one of the things that I really want to message to everybody here is engineering degree is just a starting point. And if you're looking at a potential field or an area of study, engineering is a degree or a field of study where you can really take any direction you want. So I started in engineering school, became a salesperson, and now I'm essentially a business person with with a technical aspect to what I do. So, what I enjoy about what I do now is I get to deploy our significant engineering resources really to any customer problem that either is brought to me or that I want to help solve. And, what I'd recommend and why I'd recommend Power Systems is it's the ability to really work on our critical infrastructure. It's all the stuff behind the scenes that, as long as you have your heat and lights on, you really don't think about. But as I go around town, like if we're running water in this room, I know where that water comes from, what the plant looks like, what the power is that keeps that water pumping and flowing. If you flush a toilet here, I've been to that water treatment plant. It is not quite as exciting as it sounds, but it is pretty cool to have seen the behind the scenes. If I'm at OHSU or Legacy Emmanuel Hospital, I've been involved in the critical power systems for those facilities. Even something as simple as using Google Maps or using Facebook, understanding what the critical power needs are for a data center like that, and having seen a lot of those facilities, it's very rewarding to understand and be able to see an aspect of society that a lot of people don't get to see. So with a few minutes left, want to make sure we stay on time. I will breeze through a project that is also one that is very relevant to our area. So recently worked on a project. This is Bonneville Dam. This is right off of Interstate 84, just outside of Portland. I'm sure hopefully most of you have driven by and seen it. So Bonneville Dam was built by the U.S. Army Corps of Engineers as part of the Public Works project in 1933 to 37, and its total capacity across the two powerhouses is 1.3 gigawatts, which is a tremendous amount of power. I looked this up last night, and that's enough to power approximately 500,000 homes. So what a dam is it's basically a collection of generators that convert mechanical energy to electrical energy through electromagnetic induction. Have you covered generators?
We are doing power generation next.
Okay, perfect. Well, this will be a good intro.
This is circuits tonight. So.
Okay. So the generators at Bonneville Dam produce energy at just over 13,000 volts, and they will step up at the facility to 115,000 volts or 230,000 volts. So as you drive on 84 and you pass the dam, you go right under the overhead lines that are headed up over the hillside there. The Powerhouse 1 generator circuit breakers were manufactured, they're original, in 1934, so they're 85 years old. Does everybody know what a circuit breaker does? Yeah.
Isn't it that thing in your house where like if it goes like above a certain voltage, it breaks that?
Yeah, very close. It can do that. The ones in your house respond to current. And so the purpose of a circuit breaker is to prevent fire. So the circuit breaker in your house is monitoring the current or the flow of electricity. The more current flow you have, the more what you have? Heat. So really the circuit breakers in your house, or a fuse if you have that, is really just to protect against the wires getting too hot. This circuit breaker in Bonneville Dam, which is much larger than the one in your house, is essentially doing the same thing on a much larger amount of load and much higher voltage. So these existing circuit breakers, they're filled with oil, they're 85 years old, they can't maintain them, and they don't perform very well. So our project essentially was to replace these circuit breakers, but to do so with modern technology. A modern circuit breaker for a voltage of this level, rather than using oil, uses vacuum. But the form factor of the breaker is much different. So these are very unique in that they're built into these concrete bunkers, and the new circuit breaker would be like a tenth the size. So we had to come up with essentially a way to reconnect it in this existing system while still meeting the same ratings. Making it more complicated, we actually did not originally get this order. So there was another company that came before us that put together a really cobbled together solution that didn't meet the customer's needs. So they knew us and they asked us to come take a look at it. We were able to do an inspection and perform some basic analysis to show that the assembly that was used to house these breakers that was put in really did not meet the electrical ratings that were required. So we were able to calculate the potential deflection of the internal components during an overcurrent or a short circuit and confirm that the system wasn't rated for what it needed to be. So we essentially went back to the drawing board, and a handful of my engineers took those circuit breakers out, took all of the measurements in the field, took those back to the office. We developed a 3D model in order to show the customer how we would physically connect this new breaker that sits down here and have it reconnect in the existing system for the dam. We took that to one of our manufacturing plants, which developed drawings for a real product that we could make, and then we're able to actually go physically see the initial prototype when it was built. So I took this picture at one of our facilities in Omaha. Yeah, go ahead.
How big was the initial or the previous circuit breaker? Like in terms of size comparison?
Yeah, so it's probably that cubicle is probably about 6 feet tall and maybe 8 feet or so wide. Those things weigh a ton. They're massive. The Corps of Engineers, actually, they've got these little hover pads they use to pull those things out. The breaker itself is 3,000 amps electrically, and like I said, it's a 13.8 kV. So you can calculate the amount of power that each one of those is. It's a massive, massive circuit breaker. This is what the new one looks like down here. It's much smaller. That silver cover is the circuit breaker itself. And then we added what's essentially just a switch. It's like a light switch that they can use to isolate that circuit breaker. That's the final product. And then the really cool thing, because it was a completely custom product, we had to test it to the industry standards. There's only one place in North America that you can send this. So we actually shipped this to a company called Kima Labs in Pennsylvania, where they could basically perform the test to show that this product would be reliable enough for use in the application. So that included testing it at 95,000 volts for a short period of time, testing at its continuous current, so 3,000 amps for 8 hours with sensors all hooked up to it. And then the really exciting part was short circuit testing. So essentially we connected the equipment into a short circuit of 200,000 amps for a very brief period of time. So that was the project. Thank you. Questions?
What does a typical day of your job?
Right, so the question is, what's a typical day of your job look like?
That's a great question. Right now, I spend most of the day on the phone, but I have, like I said, a team of engineers. They're very rarely in the office, so they are out working at, for example, Bonneville Dam, or they're at a water treatment plant, or they're at a hospital, and so I'm coordinating their work scope, trying to determine what we need to do, and then when they're out working, I'm coordinating with them as to what our progress is, what challenges they have, what additional support or resources they have, as well as in the remainder of the time I have looking over the financial information. So how are our projects running? Are they profitable? Are they unprofitable? What do we need to do to make them more profitable? Handling things like talking with customers, talking with our salespeople, making sure we're well positioned for future business, future orders. Yeah?
How exactly does a circuit breaker work? Like what makes it, what's the word? Protect the connections from short circuiting potential fires.
Okay, so the question is, how exactly does a circuit breaker work and how does it trip?
How much time do we have?
Answer away.
The ones in your house.
Do keep in mind we haven't done power yet,
Right.
So
the little circuit breakers in your house have a very simple element that as current runs through it and it heats up, it deflects. So it's two dissimilar metals that are fused together. When you heat them up, it bends and it hits a little bar that releases a spring and it trips. The circuit breaker in this application is much different. You do not want to run 3,000 amps through a little piece of metal and see if it deflects. So in that case, we actually have equipment that will sense the magnetic field that's generated by the current and sends that to basically a microprocessor program with specific trip levels and communications. So all circuit breakers work a little bit differently, but from a very a straightforward fashion. They're all monitoring the amount of current that flows through the load, and in some way you're releasing mechanical energy. So the breaker in your house, when you turn it on, you can feel the resistance. You're charging a spring. Same thing with that breaker, except for the springs are much, much, much bigger, because that's, like we said, 200,000 amps. It needs a ton of energy to be able to physically open that device.
Okay, so last week we were actually talking about the professional engineering certification.
Yes.
Which you very recently, or not very recently, but within the last couple of years got. Mm-hmm. Would you share with them briefly the procedure in that, or what was involved in getting that for you, and then what that certification means?
Yes. Yeah. Great question. So, if you are going to, if you're going to serve as what's called a licensed engineer, so if you're going to do any engineering that essentially interacts with like public or public safety, if you're going to design a bridge, you're going to design a roadway, you're going to design the structure of a building or the electrical system, you need to be licensed in the state that you work in. That's called a professional engineering license. So the way that you get that certification is two things. There's an initial exam that you can take. Most people take it when they are graduating from college, called the Fundamentals of Engineering exam. It's an 8-hour test that covers 4 hours of it. It's just general engineering. So you have to be able to answer everything from statics, dynamics, thermodynamics, circuits, digital design, and then 4 hours of your own specialty of choosing. So you can do, civil, mechanical, electrical, or another general test. That's probably the hardest test I've ever taken, just because it covers so much of the engineering discipline. And when I graduated from Oregon State, I thought I would never need it or never use it, so I didn't take the test when all that stuff was fresh. I took it probably only 3 or 4 years ago, so it took quite a bit of study to be able to get prepared for that exam. Once you pass the Fundamentals of Engineering exam, and you have, I believe, 5 years of industry experience, then you can apply and take the professional engineering exam, which is specific to your discipline. And again, that's an 8-hour test. I actually think because it's what you ideally work on, it's a lot easier to pass. So once you have that, then you can apply to the state that you want to work in and get references, certify that you're going to perform ethically and you're not going to design something that's going to put the public at risk, and you can get a stamp.
Fair enough. All right. Do we have any other questions for Mr. Besson? Mr. Besson, PE. Okay, great. So my question that I ask everybody who comes is, if you knew when you were in the chair that they're in right now, what you know now, what would you have done differently, or would you have done anything differently? In terms of your education, not your personal life.
Thank you for clarifying. You were already doing something differently than I did, which is I would just recommend take advantage of the opportunities that you have. Everyone here has tremendous opportunities based on where you go to school, the opportunities that are in front of you, and you're already taking time and initiative to invest in yourself and invest in your education. So that is one thing that I would do differently. It's hard when you're young to know where to focus and how to spend your time, but when it comes to things like high school and college, you have really one shot to take advantage of that and to make the most of it. So that'd be the one thing I would do differently, is really take advantage of every opportunity you have to better yourself through education. And sometimes it can seem like a grind, but it's the best opportunity for you to take advantage of that time. So that's what I do differently.
Fair enough. All right, last chance. Any questions? All right, let's thank Mr. Besson.
All right, thanks a lot.
All right, so he is going to stick around and correct me as I teach, because as an electrical engineer, he knows way more than myself at what we're talking about tonight. But tonight we're going to talk about electrical circuits. So many of you have taken physics. Lynn, I suspect that you are like an IB physics or AP physics, or you're not. So is anybody here familiar with electrical circuits? You are? Couple hands? All right. So why don't you guys tell me then, what is electricity? The movement of electrons? Right. So if we didn't have electricity, what would these lights be doing right now? They wouldn't be on? They wouldn't be giving off light. They wouldn't be giving off heat. Yeah, that's a good answer, right? All right, so yeah, very simply, for those who don't know, atoms have electrons on them, right? And those electrons can bounce off. They can move to other atoms. But what we can do is if we apply a voltage, or what we call an so they normally kind of move around like this, these little guys moving around. If we apply a voltage or an electromotive force, we can actually force them to move in one direction. So somebody remind me, please, what is the charge on an electron? It's negative charge. Yes, you're right. Yes, that is correct. But it is a negative charge, right? So, good job. So, with the negative charge, right, our electrons want to move towards what? You guys remember magnets, right? Our negative charge moves towards what? Positive charge, right? All right, good. Okay? So, charge, just like she said, just like Miss Daphne said, the coulomb is the fundamental unit of charge, which is equal to 6.24 times 10 to the 18th electrons is a coulomb. It's noticed by the capital letter C. And then if we take the reciprocal of that, the charge on one electron is 1.602 times 10 to the negative 19th. Okay, now again, I promised you guys when we started this course off, I'm not going to hide the book. You don't have to remember that, right? But if I were to ask you to calculate how much current was going through something, if you knew how much current, you should be able to calculate how many electrons are flowing that per piece of time, right? Because electric current is charge divided by time, right? So again, if I said I have so much current going through there, it's that per time unit, right? We could say 1 minute, we could say 1 hour, we could say 1 second, whatever. You should be able to calculate how many little tiny electrons went flying through this single space that we're looking at. Okay? So in circuits, a current is noted by the capital letter A, which stands for amperes. Okay, that's the SI unit, and is often abbreviated as amps. That's most often how you're going to hear it. So 1 ampere is defined as a coulomb of electrical charge moving through a given point per second. So a coulomb, remember, is 6.24 times 10 to the 18th electrons of charge. So an ampere thus is 6.24 times 10 to the 18th per second. Okay, so remember we were talking about our positive, negative. So if I have my battery, right, I have a positive side of my battery and a negative side of my battery. So which side do we think the electron's going to move out of? The negative side, right? And which side is it going to travel to? The positive side. So what would happen if I took a battery that had the negative on this side and the positive on this side, and I had one the negative on this side and positive on this side, and I put them together? What would happen? What's that? No, they're not magnets. They won't push away. But will we get flow? No? Why? What's that? Yeah, so sorry. The thumb is positive and the finger is negative. What happens if I go like this? Can it flow? We can get negative to positive, right? But if I put the two positives together, am I going to get flow? No. Okay. So again, just to be very, very clear, right, our little electron's spinning around. He's moving from the negative side of the battery to the positive side of the battery because the electron has what kind of charge on it again? Negative charge. Very good. All right, so just like force equals ma, right? If we want something to move, what do we have to do to it? I just gave you the answer, right? We apply a force, right? So what do we call a force in circuits? A push? No. We call that push, we call that force a voltage, okay? So the force that pushes those electrons is called an EMF, electromotive force, or better known as a voltage, okay? Voltage is a measure of the potential energy between one point in the circuit to another point in the circuit. So it's just like water, right? You guys are all familiar with potential energy because you guys have taken circuits, right? Or physics, sorry, right? So if I have water at the top of a hill, does it have more or less potential energy than water at the bottom of the hill? Yes, more is the correct, right? The one on the top has more, right? So which way does water flow? It flows down, right? And why is it flowing down? Because it's moving from high energy to low energy, right? And we have the exact same concept here, right? Our electrons are going to move from high energy to low energy, okay? We want everything to be equal in the world, or in the universe, okay? And volts, very simply, is noted by the capital letter V. All right, the last concept in circuits not the last concept, but the last of the three big concepts in circuits is the concept of resistance, right? So that's basically your friction in physics, right? If our ball's rolling down the hill, it's going to be slowed down a little bit by friction, or when you guys are driving your car, there's air friction coming back on you, there's a friction of the road. Resistance is that in circuits, okay? This pushback of our electrons trying to move through whatever it's moving through is called resistance. So every single material, and this is where the engineering part of it becomes important, right? Every single material, no matter what, even the air, has some inherent resistance. Mr. Besson, what is the resistance of vacuum?
Very, very high.
Very, very high. Like technically infinite, right? A perfect vacuum, or is that not true?
That would be true. Yeah.
Okay, so you guys may know this already, right? Why would I wear rubber gloves when I'm handling electrical equipment? Because why? Because it has high resistance, right? Why would I not want to wear like metal containing gloves when I'm handling it? Because it's conductive, right? The electrons are going to be able to move through it, but when I'm wearing rubber gloves, it's not. So you guys already inherently understand just from paying attention in your life that some materials conduct or resist better than others, right? So glass and plastics have very high resistance, right? Something like wood, right? If you were to plug a battery into wood, is anything really going to happen? Not really, not anything observable, right? But if you were to connect a copper wire, for example, to your battery, what would happen? Yeah, electrons move through it, it's going to start heating up, right? Might even glow if you have enough power behind it, right? Okay. So resistance is noted by the symbol R and has units ohms that are abbreviated by this little guy right here, the Greek letter, what's that guy? Yeah, so that's the symbol for ohms right there. All right, and that brings us to Ohm's law. Okay, so the study of electric circuits is all about the relationship between current, voltage, and resistance. Okay, the most basic rule in all of electrical circuits is Ohm's law. Has anybody seen Ohm's law before? You've heard of it before? All right. So Ohm's law, there's actually several different ways you can say it. The most common one is V equals IR. Remember, someone remind me, what's V? What's I? And what's R? Resistance. All right, so V equals IR means that voltage is equal to current times resistance. Or you can flip that around, right? You guys can all do simple math. Flip that around, and what we end up finding is that the current between 2 points is directly proportional to the voltage between those 2 points. And that makes sense, right? The harder we push, the faster things are going to move. Make sense? So looking at this looking at this equation, let's start to fundamentally think about this from a real-world standpoint, right? So the current going through there, if I have something that has high resistance, what's going to happen to my current, right? What happens if my denominator gets bigger? It's going to get smaller, right? So if I try with the same voltage, if I try to push something through wood, am I going to get much current? But if I try to push something through metal that has a very low resistance, what happens to current? It gets much larger, right? Smaller denominator, larger value, larger denominator, smaller value, right? All right, so if we could go to page 10, please, of your handbook. This is a very simple Ohm's law problem. Shouldn't need very long to do it, and you don't even need a calculator. If I were to hook a 9-volt battery, is it not page 10? Yeah, second edition got me. All right, it is page 16. Sorry about that, guys. All right, so if we hook a 9-volt battery up to a copper wire that has inherent resistance of 2 ohms, what is the resulting current through the wire? I'll give you 15 seconds. All right, Malika, you have it?
Yeah, I don't know the units, so the current.
Okay, so we just talked about what are the units on volts or on voltage. That was a trick question because it's volts, right? What are the units on resistance? Ohms. And what are the units on current? Amps, right? Amperes, right? Amps, the big letter A. So just to remind me, because I forget things, what does an amp actually mean? Current over time. How much current over time? 1 coulomb, right, which is a finite amount of electrons, right? Again, I'm not going to hide the book, right? But an ampere is a finite amount of electrons per 1 second. Okay? So that's what that actually means. So, all right, going back to that, so Mleka, what did you get? We have a 9-volt battery, and we have a copper wire with 2 ohms. What kind of current am I looking at?
I got 4.5.
4.5, is that what everybody else got? All right, nicely done. Good. All right, so the simple electric circuit. This forms the basis for everything that we're going to be talking about going forward today, okay? A simple electric circuit is a basic system that contains the minimum components to form a circuit. So Benjamin, you're a circuits guy. So what do I need to form a circuit? A power source. Okay, what else do I need? Daphne, what else do I need to form a circuit? A load. Very good. Is that all I need? But so that's the tricky thing, is that that is all we need, because the wire itself is actually a load, right? You don't necessarily need to have a light bulb on there. Right? You guys might have made hand warmers at some point in your life, right? Where you just connect you take a paper clip, you connect it to each side of a battery, and it starts getting warm. All right, maybe you haven't. All right, either way, but you can do that, okay? So what we need is a continuous path that allows for the movement of free electrons. What happens if I connect a wire to one side of the battery but not the other side of the battery? Nothing, yeah, everyone's shaking their head. Nothing happens. Why does nothing happen? There's no flow of charge, right? Very good. Okay, there has to be a source. That's our battery or our push. And then there has to be the load, right? Our light bulb or whatever. Okay, some elements supply energy. This would be what? What would supply energy in our circuit? The battery, our source, right? And then some consume energy. What would that be? What's that? The light bulb, which we call what? A load. Very good, sir. Okay. You guys got it. So this is a simple circuit right there on the left. We see a battery hooked up to a light bulb, and that is connected, which is why the light bulb is yellow. The light bulbs being yellow and or not yellow will matter through this presentation. And then we see what we call a circuit diagram on the right. So a circuit diagram is just a visual representation that saves us from having to draw the battery and the light every time. Okay? Mr. Besson, do you use circuit diagrams?
All the time.
All the time?
Yeah. In power distribution, they're slightly different, but
Sure. Well, and they're certainly not this simple, right?
sometimes they are.
Fair enough. All right. So what we see in our circuit diagram is do we see the V up there, right? That's right next to our load. So that little hash mark thing, the two parallel-ish lines, mark our source. The resistor, that little squiggly line, stands for our resistor. Now, that can be any resistor, right? That can stand for a light bulb, a fan, whatever, a computer, whatever, right? It just means something that's consuming energy. And then we draw that arrow to note the direction that the current is going around the circuit, okay? And that is I, which is our current. Simple enough? So this one's super simple. But what I would like you guys to do now, and I know this page is correct because I did it earlier. This is page 14, right? All right. So page 14, I would like you to draw, there should be 3 of these, okay? And I'd like you to draw a circuit diagram to represent the actual circuit shown. And then we're going to pull this guy over, and you guys are going to come draw it for me. All right, who wants to come do the first one? Thomas, you want to come do the first one for us? Sure. Okay, perfect. All right, so show us your circuit here. Okay, good. So is that what everybody else got? Now he's using this as his load instead of a squiggly line, which is perfectly fine, right? But is that consistent with what everybody else got? All right, perfect. All right, Daphne, the next one. Why don't you come do the next one for us? think it's that one? All right, so step just aside so everybody can see. Does that consistent with what everybody else got? Right, so in this case, what do we notice about these two lights, or these two resistors? They're in parallel? All right, so we'll get there in a second, but yeah, they're not in a straight line with each other, are they? Okay? All right, last one. All right, who wants to come do this one? Dustin, you want to come do this one for us? Sure? All right, perfect. All right, well done. So what we have here is we have, and there's a couple ways you could do this, right? But he has it correct. So what we have here is we have two lights that are not in line with each other that are then in line with one other light, right? So the way I did it was like this, which is perfectly, it's the same as here, but the way I did it was like this. To show that these two here are in line with that. Make sense? Okay, so very well done, guys. All right, simple enough, right? So why do we care about this as engineers? That's the question. All right, so what is before I go to it, what is a switch? Something that turns something on and off. Is that actually true? Yes, that is what I was looking for, right? Perfect answer. So you guys are both right. It does, functionally, it turns something on or off, right? But what a switch does, it's a simple component, just like the breaker that Mr. Besson was talking about, right? What that breaker does is it literally breaks the flow of current, okay? So a switch has two states. In this case, what is the switch right now? Closed, okay? And so when it's closed, what it's doing is it's allowing the flow of electrons to go through. But when I open it, what happens to my light? It turns off. And why does it turn off? Right, so now our continuous path is broken. Remember, our simple circuit requires that there be a continuous path of flow. And in this case, when we open our switch, we've broken that, but all we need to do again is close our switch and our light bulb turns back on. Okay? So, keeping that in mind, we'll come back to the switch in a second, but our series circuit, so you guys were already alluding to this a little bit ago, right? No, some of you guys know this, but a series circuit is when everything is in line with each other. So if the same electron has to go through every single load or has to go through multiple loads, then those loads are considered to be in series with each other. Okay? So in this case, if I had these three or these four lights here that are in the line with each other, if one of those lights were to break, what would happen? All of them would go off, right? So in this case, right, just like we have drawn up here, if this light were to break, these other two would turn off. And why is that? No continuous path of flow. All right? So in a series circuit, now remember, we define this because the same electron has to leave here and go around here all the way, right? Same electron. So what does that mean for each of those lights? What's the current in each one of those lights? It's the same, right? Why is it the same? Because the same electron has to go through all of them, right? Very good. So what that means from an equation standpoint is the total current in a circuit in series equals the current in 1, the current in 2, the current in 3, all the way to infinity, right? If we had infinity lights on that, the current would still have to be the same through all of them. Make sense? Okay? And then the total resistance in the circuit, going back to our V equals IR, the total resistance has to be the combined resistance of all those. So what does that mean functionally if I keep adding more and more and more light bulbs on our circuit? What happens to our total resistance? It goes what? Our resistance get really high, so then what happens to our overall current? Decreases. Very, very, very good. Okay? So all the components, no matter how many, have to carry the same current. But the voltage in a series circuit is additive. Okay? So the voltage in a series circuit, the voltage consumed by one bulb plus the voltage consumed by another bulb, and so on and so on and so on, equals the total voltage in the circuit. Okay, so if I have a battery that's, let's say, a 10-volt battery, and I have two bulbs that are exactly the same on that circuit, what would be the voltage consumed by each one of those bulbs? 5, right? 10 divided by 2. Right? You can do the math for 3, 4, 5, and so on. Right? Very, very simple. Okay? The amount of voltage lost is called a voltage drop. Right? So we might look at, if say, in a power distribution system, as it goes through the wires or as it goes through other components, we might want to know what kind of voltage we lose, because that's how much power we're going to consume. All right, so now if you go to page 17 in your handbook, please. Okay, right there you should see a circuit diagram. Now someone remind me, this circuit diagram, is this parallel or series? And why is it series? Because they're all in line with each other, right? So what I'd like you guys to do is solve this circuit. Now what that means is all of the unknowns, which in this case there's only one, which is current, but I want you guys to solve for each of those unknowns. So how would we do that in this case? Just quickly walk me through it before you guys actually go do the math. Malika, how are you going to do it?
I'm going to plug the values into the equation that equals ion.
Okay, and how are you going to get resistance?
I know resistance is the 5 ohms plus the 3
The 5 ohms plus the 3 ohms, and why do you know that?
because it's the unit resistance.
Okay, but how do we know that they're additive?
Because when you're in a series.
Very, very, very good, right? So the same electron has to go through both of those guys, which means that they add together. Okay, so in this case we have 10 volts divided by, what's the total resistance in the circuit? 8. So what's 10 divided by 8? 1.25. Is that what you guys got? Let's see if I got it. That's what I got. I got that the total current, the unknown current IT, equals 1.25 amps. All right, next, before we talk about parallel circuits, I want to talk about the junction rule. Okay? You guys know that things can't come from nowhere, and things can't just spontaneously disappear. Okay? So think about that from an electron standpoint. Any electron that goes into something has to go somewhere. It has to either go flying off or it has to go through. Okay? So from a junction rule, the junction rule basically is an accounting. It's a mass balance, whatever you want to say. It's an accounting of electrons. Every electron that goes into a split has to come out of that split. Or if it's a V, right, let's say I have 10 electrons coming in here and 10 electrons coming in here, how many electrons must I have leaving? 20, right? And vice versa, if I have 20 coming in, I have to have 20 leaving. Now the tricky part of this one is that it doesn't necessarily have to be even, right? If I have more loads on this side than this side, then more electrons may go here than there. Okay? But it's just an accounting, right? So I in equals I out. Make sense? Good. Simple enough. So what does that mean for us from parallel circuits? If I think about that, I in equals I out. So does the same so Dustin, does the same electron go through each one of those lights in this configuration? Why not? Correct. If it goes through one of them, it'll just go right back to the negative side, right? And we have that for each one of those. So if all of the, let's say in the case that all three of these loads are the same, what would be the current through each one of those guys? What's that? Well, they'll have the same current through them, right? But is it going to be the same current as the total current in the circuit? Or let me ask that in a better way. Before the split, how much current do I have right here? You see what I'm saying now? Yeah. So right here before it splits, I have if these are all equal, I have 3 times as many electrons flowing as I do if I were to measure it right here, right? Because I have this one, and this one, and this one, and vice versa. After they all combine back together, I have 3 times as many, okay? And that's the junction rule that we're talking about. All right, so parallel circuits from a voltage standpoint now, and this is where the engineering part can start to come in, is the voltage for each component in parallel is the same, right? So we did that before in series. We remembered that the voltage in the circuit was additive for each one, right? But now once we start looking at things in parallel, the voltage is the same. So these lights are actually hooked together in parallel configuration, right? Why would we do that from a functional standpoint first off? Correct, right? So in our case before, and that's exactly correct. I'm trying to go back. It doesn't want to let me go back. There we go. So in this case, if this guy breaks, what happens? Do these guys go out? No, because they still have a path. They still have a continuous path. And also, what would be another reason that we might want to put these in parallel, aside from the fact that they don't shut off?
Because if they're in series, wouldn't the voltage be equally distributed, so it wouldn't
Yes. Yeah. So what he's saying that if it was in series, the voltage would be equally distributed. So let's say we have a finite amount of voltage that we put on this side, right? And they're in series. There's 4 lights here, so that voltage would be divided how many ways? 4 ways. Instead, by connecting them in parallel, I can apply that voltage then, my voltage source, I can apply that to each one of them. Now, taking it to the next step, what's the drawback of that? What's that? You actually consume more power. Because you're consuming the same amount of voltage 4 times at the same rate, you actually consume more power, which means your battery is going to do what? Die faster, right? But if you were to hook them up in series at the same, on the same battery, you would expect them all to be a lot dimmer, right? So we might need 200 more lights in here to make it just as bright, okay? So parallel is generally the way we want to go. All right, so the resistance in a parallel circuit, first off, the current in a parallel circuit, right? We kind of talked about that already, but the current is the total of the current going through all of the individual pieces. But once we get to the resistance, I won't make you guys go through the equation. I have it here and you can go back through and look at the video. But what we see is we end up with this as our equation, okay? 1 over the total resistance in a parallel circuit equals 1 over R1 plus 1 over R2 plus 1 over blah, 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 right? All the way till as many components as you have. So in this case of our 4 lights that we're using, the total resistance of that is going to be 1 over the total resistance here will equal 1 over light 1, 1 over light 2, 1 over light 3, and 1 over light 4, right? Now they're all equivalent, which helps your math a lot. And then what you'll see a lot is in a parallel circuit with only 2 resistors, you can use your algebra to make it use that equation, which is R1 over 2, R1, R2 over R1 plus R2. Okay, and again, I'm not going to hide the book from you. If you are interested in the derivation of that, please take the time, but we are on limited time and I don't want to go through that. So let's talk through this one together. This is on page 18 of your handbook. And now we have what looks to be a very complicated circuit here, right? So what am I looking at there, J-Rom?
2 loads and a single power source.
2 loads, a single power source, and how many unknowns do I have now in this circuit?
Like 3.
I have 3, right? So we have 2 unknown currents. Are those currents equivalent? Why not? Because they're in different pathways. And what else don't we know to make that determination? We don't know the amount of the second load, right? If that second load is 2 ohms, then they would be equivalent, but we don't know that it is, right? So we have to go and use our equation for the total resistance, which someone remind me, what's that? 1 over R? Yeah, perfect. That's what I want to hear. Okay? So what we're going to do first is we're going to solve for the total resistance in the circuit. Solving for the total resistance in the circuit allows us to do what? Solve for your unknown resistor. And then we're going to be able to solve for our unknown current. Okay, you guys are getting this. Very, very good job. All right, so how am I going to solve for the total current in the circuit? Ohm's law, right? What's Ohm's law? Someone remind me? V equals IR. So what's my voltage? 8 is my voltage. How many amps do I have coming out? 6. So what must be my resistance what must be my total resistance? V equals IR. What must be my total resistance? What do you have, Ben?
Oh, I have R2. You want R2 or the sum of all?
Yeah, first off, what's the total resistance in the circuit?
2 plus.
So it's just 8 divided by 6, right?
Yeah.
Which is what? Yeah, or since we know that we're going to put it in a fraction, I actually left it in fractions just to make it easy, right? Which is 4/3. Because what's going to happen is we're going to flip that upside down, right? So now that we have the total resistance, we can then put that into our equation of 1 over RT equals 1 over R1 plus 1 over R2. And we can solve for R2. So Benjamin, you said you already had R2. What do you have for R2?
I do not have R2.
You do not have R2. Okay, working on it. All right. So let's go through and solve for R2. Does anybody have it? 2/3? So 3/4 is the total. Oh yeah, sorry. 4/3. Yes, 4/3 is the total. Four? All right, so how did you get 4? That is the correct answer. It's just through math. Fair enough. All right. Yeah, so if you go through and you solve it, what we end up finding is that R2, our unknown load, is 4 ohms. Okay, so now if we go here, right, we plug in our 4 ohms. That's why we made it yellow, as it's been solved for already. Now what do we have to do to solve for our unknown circuits, or our unknown currents, sorry. Lynn, what do I have to do to solve for I1? So can you guys, someone remind me of the junction rule. What happens in the junction rule? Correct. Everything that goes in has to come out. So if I have 6 amps coming in, what's that? If I have 6 amps coming in, it has to equal I1 plus 2, right? So I1 plus I2 has to equal 6. So if I know that I have 2 ohms there, can I solve for I1? How would I do that?
More current go to 2 times the current goes to the resistor for 2 ohms.
Okay, so which way will more current go to?
The one with less resistance.
More current will go through the one with less resistance. All right, so let's walk through this, right? So now that we've solved the above, I2 is simply Ohm's law across R2. Okay, I2 is going to equal, because remember, each one of those loads is the same voltage, right? Has the same voltage drop. So the voltage across I2 is going to be 8 volts divided by 4 ohms, which is going to equal what? 2 amps. And then by the same logic, on the other one, we have how many volts? Somebody said it? 8. So 8 volts divided by 2 ohms. What do I get there? 4 amps. All right, now we've completely solved our circuit. Now the circuits you guys will have to solve will get much more complicated, I promise you. But fundamentally, it's just the same thing over and over and over again. Okay? Any tips or tricks, Mr. Besson?
No, nicely done.
All right. I am, though, going to teach you guys a trick. What you guys will see a lot, so we use the example of this light, or these lights already, right? All these lights are the same. So there's a trick you can use instead of having to go through the process of necessarily doing all the math for the resistance. There's a trick you can use. If you see two resistors that are the same in parallel, they are the same as one resistor that is half. So those two 4s there, the two 4s in parallel, are equivalent to a 2 ohm. They're just a 2 ohm. Likewise, two 6s are the same as a 3. Two 8s are the same as a 4. So if I have two of these lights here, right, the lights that we've been using all day, if we had two of them on a circuit, what would the total resistance be equal to in that circuit? One light, right? If I have 3, what happens? What do we think happens? Do you think we divide by 3? I would say you are correct, right? So if I have 3 6s in parallel, it's the same as a 2 ohm resistor, divide by 3. And if I have 4, what do you think I do? Divide by 4. All right, so now I want you guys to go to page 19, please. And I want you guys to use your cheating to go through and solve this circuit. It's actually a process. So the arrow goes from one to other, right? So what you're doing is you're going through and reducing that circuit. So first, what we see. So what do we see here fundamentally? So Daphne, what do I have here to start? Right. So I have what we call a combination circuit. So I have what I have in series with each other. I have a 3 ohm that's in series with two 6s in parallel and a 5. So what do those two 6s become just by our shortcut? They become a 3. And then what do we do to solve for our circuit? We just add them all up. And then what do we get? No. What do I get? Come on. 11 ohms. All right. So let's just recap before we move on. Okay? So series versus parallel, right? We all know what they look like. You guys have that down. Wiring. Each resistor in series is on the same wire. And in parallel, they're each on different wires. Good enough? The voltage is different for each resistor in series, and it's the same for each resistor in parallel. The current has to be the same in series, right? Why? Because it has to go through them all. And in parallel, it's different because it can't go through them both at the same time. Okay? And your resistance, and this is the important part, so in a series circuit, the resistance increases as resistors are added. Why is that? Why is that, Elizabeth? What's that? Why would our resistance increase as we add more loads in series? It's because it's more things to go through, right? If we keep adding more lights, it's more resistance, more loads on the system. But the total resistance will actually decrease, right? We saw that in our shortcuts. If we take 3 6s, that's actually the same as a 2. So it actually decreases the total resistance on the circuit. Okay? All right, so you guys already dealt with this once before. So this is a combination circuit. So we've seen two different ways of connecting them, which are series and parallel, but most of the things you're going to see in the real world are a combination of the two. And we call these combination circuits. So in this case, what we see there, R3 and R4 are connected to each other in parallel, but the entire thing is in series. R1 and R2 are in series with the parallel component. So R3 and R4 could become, we could call it resistor R5 if we wanted to, and what would R5 be worth? Whatever the equivalent resistance of 3 and 4 is. And if they're the same, then it would be 1/2, right? Okay? So this brings us to the concept of equivalent resistance. If I have a 4 and a 4 in series with each other, what's that the same as? An 8, right? If I have a 4 and a 4 in parallel with each other, what's that the same as? And if I have an 8 and an 8 with a 4, what's that one come to? Right? The 8 and the 8 make a 4, and now we're in series with a 4. That just becomes an 8. Right? So what you're going to try to do as you guys go through and you solve these circuits is you're going to try to fundamentally reduce it all the way down to just being a simple circuit. Your dream would be to have a source, and one load on the system. So instead of having your system with all these different resistors in it, you're going to go through and reduce it down, and through equivalent resistance make it just one load on there. And then that becomes super simple to solve, because what do we have to do? Ohm's law, V equals IR, right? Okay? So on page 20 in your handbook, use your shortcuts that we just talked about to find the total resistance for the following nested parallel circuit. So what we have here on page 20 is we have two parallel circuits that are then in parallel with each other. Okay, so let's go through and solve this one. Again, you can use your cheat sheets, or not your cheat sheets, you can use your cheats. What do those two 4s become? Say it again. 2. What do the 3 6s become? 2. So I have two 4s that just made a 2. I have 3 6s that just made a 2. And now what do I have? I have, no, because they're in parallel. What do I now have? I now have a 2 that's in parallel with a 2. What's that become? Becomes a 1. So what's the total resistance on this circuit? 1. So I have all these light bulbs, all these energy consuming devices that are all together, and they're all super high resistance, but it all boils down to a much lower resistance of 1. Right? So again, that's like I was talking about. When you're solving your combination circuits, convert all your parallels to the equivalent series, sum all the series together, and then just use Ohm's law. And then if you have unknowns in there, you just have to back solve. Right? It's no different than what you guys do in algebra. It's just applying it to these systems. All right, now I want to get into kind of the more materials engineering point of this, kind of what we're going to do, how you guys are going to use this from an engineering standpoint. We already kind of talked about how we could increase or decrease the power based on how we build our circuit. But we already talked a little bit earlier about different materials having different resistances, right? So why, let me ask you a question. You go to the store and you might buy a light bulb that's 60 watts and you might buy a light bulb that's 40 watts, right? You guys have certainly maybe done that, right? What would make one light bulb 60 watts and what would make another one 40? What do you think? What do you think? Do they use different materials inside? Maybe? What's that?
Size of the length.
Yes, that's correct. So actually most light bulbs are actually made using, well, that's actually not entirely true anymore. Incandescent light bulbs are kind of becoming a thing of the past, right? But fundamentally, incandescent light bulbs all use a tungsten filament. Okay? And it's just as you said, it's the size and or length of that filament that makes the difference. Okay? So it's not lost on you guys to our discussion about the gloves and the wood, right? That some things carry current better than others, right? Materials that carry it well, like your metals, we call what? Conductors. And things that don't, things that insulate you, what would we call those? Insulators. Okay? So this comes to the concept of resistivity. So resistivity is a material property. It doesn't, so what does an intrinsic material property, does anybody know what intrinsic means? What's that? It's in there, it's always been there, it's natural. That's kind of correct. Correct, that's exactly right. It does not matter how much of it you have. Right? So if I have 10 pounds of copper, or if I have 1 gram of copper, we all agree I have different amounts, and it's going to weigh different amounts, but that material is still going to have the same resistivity. Okay, it's going to carry electrons the same. It's going to have the same ability to carry electrons regardless of how much of it you have. Okay, that's the intrinsic ability of the material. And what we see is stuff like aluminum at the top of my table here, 2.8 times 10 to the negative 8. And then if we go all the way down to the rubbers, it has 10 to the 13th, right? So let's do the quick math on that. What's negative 8? What's the difference between a negative 8 and a positive 13 exponent? A whole bunch is the answer, right? Significantly different. Significantly different, okay? So we can use resistivity to calculate the resistance of a material. And this goes back to exactly what Benjamin was saying, with the tungsten filament being different size. Okay? Resistance, and this is an equation you may want to write down because we're going to be talking about it for the next 5 minutes. Okay? Resistance is equal to the resistivity. Resistivity is marked by the little row there, times the length divided by the cross-sectional area. Okay, so that's the equation. So what does that inherently mean? What it means is our L is on top of our equation. The length is on top of our equation. So what does that mean? Does that mean more length is better or less length is better? Less length is better for having lower resistance, right? So remember, anything on top, anything in the numerator, when it gets bigger, it makes the whole thing what? Bigger. And anything on the denominator, when it gets bigger, makes it smaller, right? So what we see is something that's really, 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 really long. It's a lot harder for the electron to go from the beginning to the end because it has to fight through a bunch more material. On the flip side, if I have a wire that's this big, I have a lot less options of places to go versus something that were this big because I could go here, I could go here, I have a lot less path, right? So what we see is that the resistance will increase with length and it decreases with cross-sectional area. So what that means is functionally this, okay? So if I have, so first off, remember, we talked about resistivity. Different materials have different resistivity, right? So if I have a wire that is twice the length, will it have higher or lower resistance? Higher. Why? Because it's twice as long, right? The longer we get, the more resistance we have. But if my wire gets fatter, what happens? Resistance gets lower. Okay? And if I change materials, then what happens? Depends on the material, right? Very good. Okay? So, and in this case, right, the nickel bar there, the gray bar, it has a higher resistivity, and it's the same size, so it's going to have what? Higher resistance. Very good, you guys. All right, so last one of the day, last example of the day, course handbook page 22. Now, I have to admit there is an error in your book. Okay? The first one there that you see, the A over the L, actually has a 2L in your book. So the one that's on the top left needs to read just L. And the one that is on the bottom left, the bottom left there, in your book, it is it's the middle on the right side. Right where you have your finger there. Yeah, so the middle on the left side there's 2, and on the right side there's 3. The middle on the right side also has an L. I caught that error today while I was going through it, so I apologize. So what I want you guys to do here is, using your equation that I had you guys write down for resistance, I'd like you guys to go through and figure out which of these wires has the lowest overall resistance. Andrew, what do you think? You had to answer, but you just erased it? Yeah, this is a trick question because there's 2 of them that are the same. So Daphne, you had it. There's 2 of them. Which 2 do you think are the lowest resistance? Okay, so let's go through and do the equations. Right, this top one here, I have equals R equals rho L over A. Okay. The next one now we see is smaller because it's R equals rho over L over 2A. The third one down we see is exactly the same. We have L over 2A there. Now the next one gets fatter, but it also gets longer. So what happens? Comes out to just be L over A. And then this next guy is super skinny and super long, which is the absolute worst case scenario we can have. And he's 2L over A, right? He's the worst one we have, okay? So the lowest is which ones? The 2 on the left, right? Half the length in the area, or length with 2 times the area. Very good. All right, so what does this mean from an engineering standpoint? If we were trying to design something that would be very efficient for transmitting our electrons, what would we want to design? What would you design?
smallest amount of circuit. Like it's a small wire but fat, so it can carry the.
Small wire but fat,
Yeah.
right? And that would be very good. Now let's go to the other side. So what would we want to do, Malika? What would you do if we wanted to generate a bunch of heat? A skinnier wire but longer? Yes, that's exactly correct, right? So now let's think about that from a light bulb standpoint. If I wanted my light bulb to burn super bright, what would I do to the filament on the inside of the light bulb? I'd make it super long, super thin, right? And if I could then have a difference between a 60-watt bulb and a 40-watt bulb or a 35-watt bulb, whatever, all I have to do is just, knowing what my power source is, all I have to do is just change the size and length of my wire. You guys can use exactly what we talked about tonight to figure out what we're going to generate, right? And actually, that's not entirely true. We'll talk about power generation next week, right? The actual equation for that. But
What if you had to choose between copper and aluminum for the conductors in a building?
good question. They'd have to go back to the chart, and they'd have to look at what? What do we have to look at on our chart? Resistivity. And do you want us to be higher or lower in your scenario?
Same.
You want it to be the same?
Mhm.
Ah, okay. So you
But
now have.
copper is 3 times the price. So I also want it to be the cheapest.
Okay, so that's a good engineering problem, right? So you could either do what he was originally saying, which was, let's say we have to design 2 light bulbs that are exactly the same resistance. One's copper, one's aluminum, you said? Mm-hmm. Would those filaments be the same size? Why wouldn't they be the same size? Same resistance. They have different resistivity, correct. And then you have to go back and go report to your boss, Mr. Besson, who's watching the finances of the project, and you have to select the proper material that's going to be cheapest to work, right? Good? Mm-hmm. All right. All right, so that is all we have for the lecture tonight. We are a little longer, so I'm only going to give you guys 3 minutes. So please run to the bathroom if you need to real quick, get a drink of water, whatever you need to do, and then come back, and we're going to do tonight's lab activity, which is playing with circuits.